Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on Laplace Transformation, lecture number 6, which will include solution of some Laplace transformations of special type of functions. Now I will solve the Laplace transformation of a periodic function. Here prove that Laplace transformation of ft equal to 0 to t e to the power minus pt ft dt by 1 minus e to the power minus pt, where ft has a period t greater than 0. Now, since given that ft is a periodic function, ft is a periodic function with period t, that means ft plus t equal to ft. After t interval, the function again return to its original value ft. Now we find Laplace transformation of ft. L ft equal to 0 to infinity e to the power minus pt ft dt. This will be equal to 0 to t e to the power minus pt ft dt plus integration t to 2t e to the power minus pt ft dt plus 2t to 3t integration e to the power minus pt ft dt and so on. Let this is I1, this is I2, this is I3 and plus dot dot dot. This is number 1. We solve I2, I3 sequentially. Here, let for I2 we calculate. Let t equal to x plus t. When lower limit is t, value of small t is capital T. When t equal to capital T, then x equal to, here capital T cancel, x equal to 0. When t equal to 2t, here 2t, if we put 2t, then x equal to t, then x equal to t. Also dt equal to dx. So I2 equal to, now we use the variable x here in place of t. So value of x is 0, lower limit 0, higher limit t, e to the power minus p, t means x plus t, f x plus t dx equal to 0 to t e to the power minus px e to the power minus pt ft plus capital T equal to ft, then fx plus capital T equal to fx, as f is the periodic function. So this will be fx dx equal to e to the power minus pt 0 to t e to the power minus px fx dx equal to e to the power minus pt 0 to t e to the power minus pt. We may change the variable of definite integration x by t. So I2 equal to e to the power minus pt 0 to t e to the power minus pt ft dt. Now find I3. We find I3. For I3 let t equal to x plus 2t. When small t equal to 2t here, then x equal to 0, then x equal to 0. When t equal to 2t here, when t equal to 3t, then if we write here 3t, x equal to t, then x equal to t. So I3 equal to value of x is 0 and t here e to the power minus p, t means x plus 2t, f x plus 2t dx dt equal to dx equal to 0 to t e to the power minus px e to the power minus p into 2t. If the function is periodic, then fx plus t equal to ft fx, fx plus 2t also equal to fx, because period is t. fx plus t after t interval it comes back to the original function fx. So we write here fx dx equal to e to the power minus 2pt 0 to t e to the power minus px fx dx equal to e to the power minus 2pt 0 to t e to the power minus p small t f small t dx dt. We replace the variable x by small t. So this is number 3. So we will get similar result for I4 e to the power minus 3pt 0 to t e to the power minus pt ft dt and so on. Now we put values of I1, I2, I3 and so on. As LFT equal to I1 plus I2 plus I3. I1 is integration 0 to t e to the power minus pt ft dt. I2 is e to the power minus pt 0 to t e to the power minus pt ft dt. I3 is e to the power minus 2 pt 0 to t e to the power minus pt ft dt. We take common, this part is common in every integral, every terms. So here remains 1, here remains e to the power minus pt, here remains e to the power minus 2 pt, and so on. This is binomial 1 plus x square. This is equal to 1 minus x to the power minus 1. Using that formula, here we get this. So power minus 1, then this is 1 by 1 minus e to the power minus pt. Hence proved. Now we solve a problem related to periodic function. Sketch the graph of the function ft equal to sin t when t lies between 0 and pi, and ft equal to 0 when t lies between pi and 2 pi. This is extended periodically. Which period? 2 pi. And find LFT, Laplace transformation of ft. As we sketch the graph, sin 0 equal to 0, we start here. Then up to pi, we may draw this graph. At pi by 2, it is 1. Then from pi to 2 pi, function of t, ft equal to 0. Here 0. Again it starts from 2 pi to 3 pi, we get similar type of result as 0 to pi, and then function value 0, then again we repeat this. This is the graph of the given function, which period 2 pi. Since Laplace transformation of a periodic function ft, which period t is given by, we just solved this formula. Ft equal to 0 to t integration e to the power minus pt ft dt by 1 minus e to the power minus pt. Here period is t, so in place of t we write 2 pi. Now we divide this integral in two parts, 0 to pi and pi to 2 pi. Here from 0 to pi, function of value of the function ft equal to sin t, and from pi to 2 pi, value of the function ft equal to 0. Now we put the value of the function ft between 0 to pi, this is sin t, here sin t, and value of ft equal to 0 between pi and 2 pi, this is 0. So this term vanishes, only remains this term 0 to pi e to the power minus pt sin t dt. The integration value is of this 0 to pi e to the power minus pt sin t dt is e to the power minus pt under bracket minus p sin t minus cos t by p square plus 1, and this is outside. So if we put the value of t first pi, then minus t, value of t is 0, and we get this result. So we solve this. LFT equal to 1 by e to the power minus pt 1 minus e to the power minus pi p by p square plus 1. Now we shall prove the initial value theorem. Initial value theorem is limit t tends to 0, capital Ft function of t equal to limit p tends to infinity p small fp, where small fp is the Laplace transformation of capital FT. Proof. Since Laplace transformation of derivative is P L FT minus F0 equal to P, this is small fp minus F0, and here we may write 0 to infinity e to the power minus pt f dash t dt. That's right. Taking p tends to infinity, limit p tends to infinity 0 to infinity integration e to the power minus pt f dash t dt equal to limit p tends to infinity p small fp minus f0. Here we see that if p tends to infinity, then e to the power minus pt is 0, because this is 1 by e to the power pt and 1 by e to the power infinity. So we write 0 to infinity, this is 0 f dash t dt equal to limit p tends to infinity p fp minus f0. Left side 0, limit p tends to infinity p fp minus f0 implies that f0 equal to limit p tends to infinity p ft. We may write this limit t tends to 0 ft equal to limit p tends to infinity p fp. It is said to be initial value theorem because limit t tends to 0, initial value of capital FT is limit p tends to infinity p Laplace transformation of capital FT. Now we shall prove the final value theorem. To prove limit t tends to infinity function of t capital Ft equal to limit p tends to 0 p fp, where fp equal to Laplace transformation of capital Ft. Proof. Since Laplace transformation of f dash t means derivative of ft equal to p l ft minus f0 implies that 0 to infinity integration e to the power minus pt f dash t dt equal to p, this is small fp minus f0. Taking p tends to 0, p tends to 0, limit p tends to 0, 0 to infinity e to the power minus pt f dash t dt equal to limit p tends to 0 p fp minus f0. Here it p tends to 0, not infinity. P tends to 0. If here p equal to 0, then e to the power 0 is 1. So remains 0 to infinity. This is 1 f dash t dt equal to limit p tends to 0, p fp minus f0. Integrating this means ft, integration of f dash t is ft, 0 to limit infinity equal to limit p tends to 0, p fp minus f0, implies that limit t tends to infinity ft minus f0 equal to limit p tends to 0, p fp minus f0. Both sides minus f0 cancel, so we get limit t tends to infinity ft equal to limit p tends to 0, p fp. As value of t is infinity, so it is said to be final value of ft. This is equal to limit p tends to 0, p fp. This is the final value theorem. Now we solve a problem of Laplace transformation of SI function. SI function is 0 to t integration sin u by u du. Let ft equal to 0 to t sin u by u du. Then f0 in place of t we put 0, 0 to 0. This gives integration 0. And f dash t, differentiation of this, sin t by t. Let we consider LFT, Laplace transformation of ft is small fp. Here we take t f dash t equal to sin t. We use Laplace transformation in both sides. That is multiplication by t. Multiplication by t is minus 1 to the power 1 d by dp, Laplace transformation of this function f dash t. Laplace transformation of f dash t is p fp minus capital F0. Here Laplace transformation of sin t equal to 1 by p square. So we get here f0 is 0. So putting f0 equal to 0, we get the next step. This. Now d p fp equal to 1 by p square dp and minus sign this side. We get p fp equal to integration of 1 by p square is tan inverse p plus constant. This is number 2. Now we find the value of the constant c. By initial value theorem, we know that limit t tends to 0 ft equal to limit p tends to infinity p fp. Here f0 is 0, so we put here 0. Limit p tends to infinity p fp. This is number 3. Now use both sides. Limit p tends to infinity in equation 2. We get limit p tends to infinity p fp tan inverse infinity. Tan inverse infinity is pi by 2. This is minus sign plus c. And this value from 3 we get 0. So c is pi by 2. Putting the value of c in equation 2, pi by 2 minus tan inverse p, that is cot inverse p. So Fp remains this side, P this side, 1 by P tan inverse. Cot inverse P means 1 tan inverse 1 by P. Now we shall solve number 6 problem. It is the Laplace transformation of error function root over t. This equal to Laplace transformation of 2 by square root phi integration 0 to square root t e to the power minus u square du. We have to prove that this equal to 1 by p into p root square root p plus 1. Now, Laplace transformation of error function is a, let this 2 by square root phi, this integration 0 to square root t, we expand e to the power minus u square. This is 1 minus u square plus u to the power 4 by factorial 2 minus u to the power 6 by factorial 3 and so on. Now we integrate this. Integration of 1 is u, 1 du is u. Integration of u square is u to the power q by 3. Integration of u to the power 4 is u to the power 5 by 5. Here factorial 2, so you will write factorial 2. U to the power 6 in integration, u to the power 7 by 7. Here factorial 3, then here factorial 3. Limit 0 to square root t. We firstly put limit square root t. Here we get is t to the power half, t to the power 3 by 2, t to the power 5 by 2, t to the power 7 by 2, and so on, minus we put value 0, u equal to 0, u cube equal to 0, u to the 5 is 0, this is 0. So we get here 2 by square root phi, we take outside and then remaining terms. Laplace transformation of t to the power half is gamma function 3 by 2 by p to the power 3 by 2. Similarly, Laplace transformation of 3 by 2 is gamma function 5 by 2 by p to the power 5 by 2 and so on. Here we put the value of gamma function 3 by 2. Gamma function 3 by 2 equal to half into gamma function half. Value of gamma function half is root pi. Value of gamma function 5 by 2 is 3 by 2 into half into gamma function half, that is square root 5. And in this way, the remaining are solved. Now we take here square root pi into square root pi, here square root pi cancel. If we take common square root pi and half, then this term cancel. The remaining terms are 1 by p to the power 3 by 2 minus 1 by 2 p to the power 5 by 2. Next 1 into 3, 2 into 4, p to the power 7 by 2, and this way. Here we take common 1 by p to the power 3 by 2. Here remains 1, here minus half into 1 by p, here 1 into 3 by 2 into 4, 1 by p square. Here we get minus 1 into 3 into 5, 2 into 4 into 6, 1 by p cube, and so on. This is the binomial expansion of 1 plus x to the power minus half. So here x, value of x is 1 by p to the power minus half. So we get 1 plus p to the power minus half, and here p to the power minus half. P to the power 3 by 2 and p to the power minus half becomes p, and here 1 by 1 plus p to the power 1 by 2. This is 1 by p into square root p plus 1. Thank you for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.